All right, sorry for the delay there. We sort of got some practice with solving three-dimensional problems looking at the infinite spherical well, which is already complicated, at least in the L not equal to 0 case. But we've seen, a lot of the work has been done, and we really just need to solve that radial equation in which the potential appears, right? We've already got the theta and phi dependence from the spherical harmonics. As long as your potential is only a function of r, that work is done. And now the only remaining work is to put in your potential into the radial equation. So here we're talking about the potential energy between an electron and a proton. That's a hydrogen atom, right? And we're going to pretend, this isn't exactly true, that the proton is what, like 2,000 times as massive as an electron. So when the electron's orbiting the proton doesn't move much classically. So we're going to pretend it's fixed at the origin, and the potential energy represents the potential energy of the electron-proton system as a function of the electron position. And from physics 230, that's that electromagnetic K, which is 1/4 pi epsilon 0, times Q1, Q2 over R. And in this case, the charge on the proton is little e, charge on the electron is minus little e, so we get a minus little e squared. And we plug that into our radial equation, which you may remember has this sort of kinetic looking term. And then there's the effective potential. And I guess I should mention a little bit. Do you guys talk about effective potential for those of you who took advanced mechanics? I'm assuming you talk about it in there. The idea is, if you think of something orbiting another object, Earth orbiting the sun, or you going on a merry-go-round spinning in a circle, right? If you're not spinning at all, that's the case L equals 0. This L we're going to see corresponds to orbital angular momentum. So L equals 0 means 0 orbital angular momentum. The effective potential is just the regular old potential. And in that case, you would say, okay, that's like being on a merry-go-round, and there's no problem walking towards the center. Or if Earth is orbiting sun, but here we're imagining it's not orbiting at all, it's going with 0 velocity, so it's just sitting there, right? The only potential energy that you effectively feel if you're riding along with Earth is the potential energy, gravitational potential energy, the usual V of R. So that would be something like this, but the gravitational analogy to that. Whereas if you're spinning around on a merry-go-round, right, in addition to the potential energy, just to stay at a certain radius of orbit, you have to have a force towards the center. Like I might have to be holding onto a rope as I'm going around on the merry-go-round. And I think of that force as being associated with the potential energy, right? I think, oh, okay, I've got to pull in this direction, or something is pulling on me, and there's a potential energy associated with that. Now, there's not actually any potential energy associated with it. It's because you're viewing things from a non-inertial reference frame. But you can think of this term as characterizing the faster you are rotating around. In other words, little l, the bigger little l is, the more angular momentum you have, the harder it is to get towards the center. It's like there's some additional potential energy repelling you from the center. Repelling because it comes in with a plus sign here rather than the minus sign. This is an attractive potential energy. This is repulsive, and it means it's when you're spinning in a circle around something, it's really hard to move towards the center. As you get closer and closer in, you're spinning faster and faster, and it's really hard for you to get close to the center of rotation. Several of you in reading responses asked about the effective potential, and that's the idea. It's when you're moving with the thing that's going around in a circle, this feels like it's your potential energy. Now, we know from Newton's point of view, that's a non-inertial reference frame. You're sort of accelerating as you go around. And so we wouldn't say this is really part of the potential energy. The potential energy is just the forces we normally see, and this is the only part that's a real force. But in order to stay on a circular orbit, you have to apply an additional force towards the center, or you feel like you're being thrown outward due to that fictitious centrifugal term, or centrifugal force, which corresponds to this centrifugal term. In any case, this is our radial equation. We're just going to think it's a differential equation, kind of a monstrous differential equation, and we got to solve it now. And we're going to do that in steps to try to simplify it as much as possible before we get a series solution. Okay, you might just say, well, let's try to get a series solution. And you can always do that. You know, if we try to get a series solution, you're going to get some very unfamiliar kind of recursion relation for the coefficients in your series solution. And you'll end up with a function that you've never heard of before. You can give it a name. You can always name a series that doesn't match with any other series that you've gotten before, but you'll have very little insight into it. So by doing this pre-preparation, we're going to turn the solution into something that formed out of pieces that we actually understand. Now, let's look for the bound states. For the bound states, we're talking about, why are the bound states less than 0? Well, if we look at the real potential energy, not the effective potential. Uh-oh. Let's refocus the camera here. Our potential energy, which is K Q1, Q2 over R, V as a function of R, the real potential energy, not the effective potential, is negatively proportional to 1 over R, right? It's minus K E squared over R, right? If I put in the two charges, E and minus E, and K is 1 over 4 pi epsilon 0. So that means energies down here are going to correspond to bound states. And if the electron has an energy up here, that's going to correspond to a scattering state. So we're going to start out looking for the bound states, which are the ones you concentrate on, and mostly the ones we're concerned with, because when we talk about an atom, we're not talking about a proton and an electron that's zipping by under the influence of its force. Usually we mean it's bound in some state. So we're still out of focus a little bit. That's better. Okay. Okay, so bound states correspond to energies less than 0 in this case. Now, if the energy is less than 0, usually the way we proceed is to multiply, or divide by this constant on both sides to get the second derivative by itself. And when we divide by this, in other words, multiply by minus 2m over h bar squared, we get a minus 2me over h bar squared. But E itself is negative if we're looking for bound states. So minus E is positive, right? And so we make that usual definition. Let's define kappa to be the square root of minus 2me over h bar. In other words, the square root of the thing that appears on that side after we divide by those constants in front of the second derivative. And for us, that's just a simplifying thing, right? We're going to go back. We'll be interested later in the energies. So we have to remember things will be written in terms of kappas. And in fact, we'll make several other variable transformations to make our life easier. But ultimately, we're going to be interested in the energies. So we're trading those out for kappas now. Here's our first other of the other transformations. We're now going to change the independent variable here. So right, you have U is the dependent variable of the solution, and U is a function of R. That's the independent variable. And to simplify things, we're going to change it to be a function of rho, which is kappa R, defined as kappa R. And worksheet 1 is, Griffiths doesn't really say anything. He just tells you what the solution is. So let's try to do this. And I want you to think about it for a couple of minutes and see if you can start doing that. I want to write this second derivative with respect. Originally I'm thinking of U as being a function of R, but now I want to think of, well, if U is a function of R, U is also a function of rho, where rho is kappa R. How do I write this in terms of a second derivative with respect to rho? Well, you got to use the chain rule. Just meditate on that for a couple of seconds and see if you can eliminate all the R's from this equation and exchange them out for rho's. Now it's easy right here. R is just the same thing as rho over kappa. So that one's easy, that one's easy. But you got to think about this derivative. How do I write a second derivative with respect to R in terms of the second derivative with respect to rho? And I believe, well, I'm hoping this is on the website. Alvis, you can tell me if that's true.
All right, let's see.
It's either for yesterday's date or today's date. I can't remember. If it's not, I will quickly email it to you. But
All right, let's see.
I thought I put it on.
Should be. Where is it again?
It should be either under yesterday's date or today's date. I've got
I
my
see
lap.
one from the other. I don't see one from yesterday or today.
Okay, well, luckily I have my laptop here because of my drive problem, so I'm just going to email it to you.
Oh wait, is it the chapter? No. The only thing we have for today, or that's homework.
Sorry about that. Sometimes I get too busy and forget everything that needs to be done on the website ahead of time. So let's see. Well,
Is it the worksheet from today's class on 4.5? I thought we finished that.
it should say hydrogen at the top.
Okay,
And
then no, you don't have it up.
I just emailed it to you, so you should have it in your inbox now. Sorry about that. So we're doing
course.
problem 1 on there.
We got it, I think.
Thank you.
Hold on. Let's see. Yes, this is it.
Thank you.
Sure. Okay, I'm not sure how it's going, but the most important step is the first step, which is converting that derivative. Then it's just a matter of kind of simplifying things. And so it comes from the chain rule when we want to change what you're taking the derivative with respect to. Now, in this case, because rho is just kappa r, you might be able to guess how to change it. But if rho were e to the r, it might not be as obvious how to change it, but the chain rule tells you how to do it. Every one of you knows how to take the derivative of a function of r, right? What do? We first take, we think of this as just being some blob here, and the derivative of the sine of blob is the cosine of that same thing back again, times the derivative of this thing with respect to r, right? So we're going to think of this as like our rho of R. This is the derivative of the sine of rho with respect to rho, right? We're taking the derivative with respect to this thing times the derivative of rho with respect to R. That's the chain rule, just written out in symbols, but every one of you knows how to do that intuitively, but sometimes people forget abstractly how to write it. So for us, if we want to, we're working on this second derivative, which is, I'm going to do 2 steps at a time. The derivative with respect to R of the derivative with respect to R of u of R, but I'm going to write u of R as u is really a function of rho, which is a function of R. Right, here's my outer function and here's my inner function. And let's forget about the second derivative. We can just deal with that, the derivative on the outside we're just going to deal with later. So that's the derivative with respect to R. And on this inner one, I would say, well, what I do is first take the derivative of this function with respect to this thing, which is rho. Derivative with respect to rho of u multiplied by the derivative of rho with respect to R, which in this case, rho is kappa R. So the derivative of rho with respect to R is kappa. And when I do that, I do that the second time, I'm going to find out the second derivative here is equal to the second derivative of u with respect to rho times kappa squared. Right, each time I'm going to get one of those kappas from the chain rule. And you might have guessed that, sometimes people, when they look at, I'm going to take a derivative with respect to R, and R is rho over kappa. They just going to say, well, that's going to give me 2 factors of kappa. But if this were a more complicated function, that trick is not going to work. And you really shouldn't be just substituting variables in a derivative term anyways. But the chain rule tells us how to deal with it. So our second derivative turns into this. And the rest of the stuff in the differential equation is just easy to substitute there. So let's go back and hopefully I've got the result here. We wrote d squared u dr squared as kappa squared times d squared u d rho squared, and then put everything else on the other side and divided by kappa squared in there. And at this point, to simplify things, there's going to be 3 terms that are multiplying u, which we're now thinking of as a function of rho, right? Our solution is going to be u of rho. There's a whole bunch of constants that appear in this term that's proportional to 1 over rho. So everything that's not a rho in this thing, Griffiths defines as rho 0. Rho 0 is me squared over 2 pi epsilon 0 h bar squared kappa. That's yet another definition that's sort of compressing down things and making our differential equation looking more simple. Okay, so we changed our independent variable there, and we've somewhat simplified this. And now you might say, well, let's do a series solution now. If I don't recognize that differential equation, maybe I just go ahead and do a series solution. Well, again, you could do that, but the solution you get, again, wouldn't give you as much information because we can extract more about functions we already know about. This solution here is a combination of functions we know about, but if we write it as a series solution, we'll never be able to see those pieces emerge. So the next step is the following observations. Griffiths looks at this differential equation. He says, well, what happens when rho is really small? Okay, rho is proportional to R. So that's like saying, what happens at really small radii? Well, when rho is really small, this term's huge, right? Because I'm dividing by rho squared. So I can ignore these 2. And then I get a very simple differential equation. Also, what happens when rho is large? When rho is large, these 2 terms are ignorable compared to the 1 over there. And we can see what sort of behavior it has for large rho and small rho. And so just thinking about those more simplified differential equations, you can see when rho is small, you get a power kind of function, right? That u of rho is proportional to rho to a power L plus 1. And if rho is large, again, simplify the differential equation, throw away the terms that you can ignore, and we find out that u of rho is proportional to e to the minus rho. Okay, so we've got these interesting behaviors for small rho and large rho. And that kind of motivates, well, let's change things again, not the independent variable, but this time the dependent variable, u. I'm going to say our u, which is a solution, let's factor out a rho to the L plus 1 times an e to the minus rho, and write whatever's left after factoring those out as v of rho. And we're going to change the dependent variable to v. In other words, I got a differential equation for u. I now want to convert that into a differential equation for v. Now, this one's pretty easy to think about how to do, although it's a little bit more of a mess. So I decided let's do this one together. I'm just going to show you my solution here on the slides for this. Here's our differential equation for u as a function of rho, and we want to rewrite it as a differential equation for v as a function of rho, where this is the relation between u and v. We've just factored some stuff out, and what's left is v, and that gives you a u. Well, the hard thing is this second derivative again. When I write, okay, so let's do the first derivative of u with respect to rho. When I take the first derivative with respect to rho, when I do it to this side, I have to do a product rule, right? I've got a product of three things. I can put the derivative on the v, and then I've got the other stuff just multiplying it. But then from the product rule, I've also got to do just v sitting there times the derivative of this. And I've got a product rule, I've got to do that. So I do that derivative of this product and then simplify it, factor out the common factors that result there. It's nothing but taking the derivative of this with respect to rho. Then we have a second derivative. So I got to take the derivative of this mess with respect to rho, which then turns into kind of a real mess. I've got to take the derivative of this with respect to rho. Well, that again is a product rule, and this, there's a product rule there. And that gives me four different terms here, which are kind of a mess, at least initially. And then I'm going to collect together terms. I've got a v term, which I can try to simplify. I've got two dv d rho terms, which I can try to combine together and simplify. And I've got one d squared v d rho squared term. Okay, so it's, you know, you have to do a little bit of work there. When you do that, you can put those together up here and write that in for what d squared u d rho squared is. And then the only thing that's left to do is to work on the right-hand side. Well, of course, u, I can just substitute as rho to the L plus 1 e to the minus rho times v of rho over there. And when I do that, I can factor out, you know, so I've got powers of L I'm putting over here in u. I've also, sorry, powers of rho, which I've got over here in u. And I've also got powers of rho inside this piece here. And I can sort of combine them together and factor out a factor of e to the minus rho times rho to the L plus 1. This is what's left in there. Not a lot of interesting stuff going on here, but it's just, you know, you have to follow through the details. So putting that all together and putting everything on one side of the differential equation, here's what you get for the differential equation for v as a function of rho. And you might say, well, it looks like we're losing ground here. It's more complicated than the one we had before, but we'll see why factoring out those two behaviors really helps us in this case. Okay, so that's problem 2, turning it, you know, changing the dependent variable from u to v by factoring out those things. Now, after doing that, you know, this isn't obvious to begin with, but through many people working through the same problem, you start to see ways to simplify things and get simpler looking solutions. Now we're going to try a series solution, okay? So I write a generic power series, and I substitute that in, differentiating term by term for the derivatives. And then you remember the technique of saying, like powers have to have coefficients that, in this case, all the coefficients of all the powers are 0, And so if I add together all the coefficients of each power of rho on this side, it's got to be 0 too. And from that, you obtain a recursion relation. And in this case, it's not too complicated. It's a first order recursion relation, which means Cj plus 1 is just proportional to Cj. And if you can solve that recursion relation, then you effectively can figure out what this function is. It's like summing the series. In this case, we're not necessarily going to do that, but rather, again, some smart person has said, well, let's look at these coefficients. How Cj plus 1 is changing relative to Cj. And we can see that at least when j is large, again, when j is large, you could simplify this down by keeping only the most dominant terms when j is large. When j gets large, v of rho behaves like e to the 2 rho. Well, rho is proportional to r. So this is a function that's exponentially getting bigger and bigger as r goes out. We're not going to get a normalizable solution. We're not going to get a bound state solution. Our bound state solutions definitely have to go to 0 as it gets large. The other two factors aren't going to help here. We've got an e to the minus rho factor, which looks sort of hopeful, but here we're getting, if this behavior is like e to the 2 rho, it dominates that and makes it blow up when we consider multiplying all those together. So that's sort of disappointing, because that means v will have this behavior, and that means u will be non-normalizable. And if u is non-normalizable, r is just u over r, little r. So that's going to be non-normalizable as well. It's going to diverge exponentially. And you might throw up your hands, but there is another option. The other option is that, well, what happens if the series terminates? In other words, from this recursion relation, you can see if some Cj happens to be 0, well, automatically Cj plus 1 is 0. And that means Cj plus 2 is 0. And Cj plus 3 is 0. And this function will be a polynomial rather than this e to the 2 rho kind of function. And if you have a polynomial, now polynomials still diverge as they go off to infinity, but that's not the only piece. We're talking about v being a polynomial. So this is a polynomial. This is a polynomial in rho over here too. So we've got a polynomial times e to the minus rho. Polynomial times e to the minus rho will actually go to 0 fast enough to be normalizable. So if this series terminates, then we're good to go. We have actually a normalizable solution. And you can see now the benefit of factoring those things out. We've just found out, and we're going to solve explicitly for what these polynomials are. This is a polynomial. Here's a power function. That's a kind of polynomial. Here's an exponential function. We've gotten the solution for u as a function of rho, and then I can substitute for rho as a function of r, and then I can change u into r of r. We're going to be able to write it in terms of explicit functions that we know of those types. Rather, if I had done a series solution right from the beginning, I would have just had some series I don't recognize. It would have had this behavior in it, but it's nice to be able to know that behavior and see it explicitly, rather than just having it encoded in some mysterious series. Okay, so we're going to imagine that there's some j index here, which is the largest non-zero Cj that appears, right? And Cj plus 1, or C, if we call that index j max, so we're imagining Cj max is not 0, but C j max plus 1 is going to be 0. Right? But that's what defines that maximum index. Then we want to see what that tells us about the relationships between these other constants in here. So I'm looking at problem 3 now. I've given you there the recursion relation. And you're just going to require that when I plug in C j max and require that that's not 0, but I want C j max plus 1 to be 0, what does that tell me about the relationship between j and L and rho 0? So that's problem 3 we're thinking about now. Okay, as you can see by the space there, there's not much work to be done for this one, but let me write down my recursion relation up here on the board. C j plus 1 is equal to kind of a mess. 2j plus L plus 1 minus that combination of constants rho 0 divided by j plus 1 times j plus 2L plus 2 times Cj. Okay, and we're going to imagine the case where we want Cj max plus 1 to be 0. In other words, Cj max is not 0, but we want Cj max plus 1 to be 0. That's what the symbol max means, right? It's the last non-zero one. So all I'm doing is substituting j equals j max in here. So I got to put a max on all of these j's. And I want, if this is the last non-zero one, then that means this one is equal to 0. So this whole thing is equal to 0. Now, I've got a product of a bunch of stuff equaling 0. This one's not 0 by definition. We're saying this is the last non-zero one, right? This is not 0. What about the denominator? Can the denominator ever make a ratio equal 0? No, there's nothing you can divide by to make the numerator equal 0. Divide by 0, you're making it go off to infinity, right? And whatever number you divide by, 0 or not, then it's not going to make the ratio itself go to 0. So if a ratio is going to go to 0, this means the numerator has to go to 0. 2 times j max plus L plus 1 minus rho 0 is equal to 0, or this is equal to rho 0. Okay. So that's the relation that's being suggested there, and we're going to use that fact. Okay. So here's our result, that rho 0 has to be this combination of stuff. There's a suggestion, let's rename j max plus L plus 1 as a new symbol n. I know this is like the 4th renaming of things in here. But this is your old friend n, that quantum number that you know from the hydrogen atom, right? That determines the energy level. You can see n as an integer, right? Because the j's are integers and the l's have to, we already found out, have to be integers. So at least we know n is an integer. So that kind of makes sense, right? Let's just take that at face value. We'll find out the range of allowed n's later on. But let's define n to be j max plus L plus 1. And therefore, this is just n here. Rho 0 is 2n. All right, there's a lot of definitions that are piling up, but let's keep that one in mind. Rho 0 is 2n. Now that we found that, let's figure out what the bound state, allowed bound state energies are in terms of n. And this is one case where, well, this is a hint here. the pieces that you need to look at are here. This is part of what I couldn't get from my other set of slides. But remember, we made our definition that kappa is the square root of minus 2me, because E itself is less than 0 over h bar. And if I solve that for E, that gives me this relation, okay? So there's my fundamental relation that tells me about E. But now what's kappa? Well, let's see. We made this combination of constants, kind of ugly, for rho 0 in terms of kappa. So I can solve that for kappa in terms of rho 0, right? So substitute that in there. We just found out in order for the series to terminate, rho 0 has to equal 2n. So let's substitute for rho 0 in terms of n. I want you to put those two substitutions in there and get an expression for E as a function of n. And you will see an old friend, hopefully, from modern physics staring you in the face. Okay, so again, there's just a couple of steps. You have to write down a lot of symbols, but I'm going to say, if I solve this for kappa, I get kappa is this stuff with a rho 0 in the denominator. Substitute that in there and square the whole big mess, ratio mess. That will be written in terms of rho 0, and then I substitute rho 0 is 2n and try to get everything factored out of the n dependence. And here's what results. Of course, we got that overall minus sign out in front because kappa is being squared, rho 0 is going to be squared, and that means n is going to be squared. So, and the rho 0 is in the denominator, so I get a 1 over n squared, and I'm just going to put all the rest of those constants in parentheses there. And that is that number that if you put them in electron volt units, you get 13.6 eV, which hopefully you remember from modern physics as this is sort of just in a nutshell. You know, if you think of minus 13.6 eV over n squared, those are the allowed energies of the hydrogen atom. That 13.6 EV comes from all those constants put together. Okay, so we found the allowed energies. Now I realized there were like 4 substitutions of variables deep in there, so I wouldn't consider it intuitive, and we still have to figure out, well, what are the allowed values of n? By definition, n is an integer, but who knows what n values are even allowed? We'll find out in just a second. That's the subject of the next thing. Okay, so we found out that these are the allowed energies expressed in terms of that parameter n, which at least we know is an integer. And then if I put the whole product solution together, right, what I found out is that we found V of rho. Those are polynomials, right? Because they are Taylor series or power series that terminate. And when you have a power series that terminate, you're talking about a polynomial. So V of rho is a polynomial times rho to the L plus 1 times e to the minus rho. That's U of rho. And then to get R of R, what I do is re-express this stuff I substitute rho equals kappa R, okay, into those. And then I have to divide u by r. That's what this 1 over r is out in front. So this is just r as a function of r once I substitute rho equals kappa r in there. Times my spherical harmonics, which come along for the ride. Remember, it's a product solution. It's a separable solution. Okay, so there's my psi. And my psi depends on this quantum number n, but it also depends on L and M, which tell me which spherical harmonics we are talking about there. Okay. So given that, now the last question is, what are the allowed ranges for N, L, and M? And this ends up being a non-trivial kind of question, although the pieces aren't too hard to put together. You just have to have everything lined up. So that's the idea of worksheet number 5. This is, something that, again, when you're reading through it, if you don't get out some paper and think about what every claim Griffiths is making, it may not be true. So 5A and B are just reminding ourselves of what do we know so far about the allowed ranges of L that we got from separation of variables. And in B, what are the allowed values of that integer M that we've gotten from separation of variables? Let's start with those. And C is asking, what's the smallest possible conceivable value for J max? What do you say to C? What's the smallest J max could be? Zero, right? If it's 0, then that means this polynomial we're talking about is a constant. It better not be 0, because if J max were -1, then there's something like that, right? If in the first term were 0, then the whole function would be 0, and then the product solution would be 0, and that would mean we wouldn't have a normalizable state. So at least one of them's got to be 0, non-zero, and the smallest we can have for the last non-zero one is the constant term. So the answer to C is the smallest possible value for J max is 0. Now I want you to think about the statement below that in C, and then D and E, and see if you can get the allowed ranges for L and N from that reasoning. I'm not claiming it's intuitive, but you're just following the facts here. Okay. Let's think about that second part of C. Given that J max is 0, the question is, and given the definition of N, this is what defined N right here. What is the largest allowed value for L? Okay, so if we want to find out about the largest allowed value for L, let's solve for L. L is equal to N minus J max minus 1 And we just determined that the smallest value for J max that it could be is 0. We got to have at least one term non-zero. Well, if I want to make L as large as possible, I'm going to want to make this thing that I'm subtracting off as small as possible. And that means I should take the minimum value for J max. And so L max is going to correspond to the minimum value of J max here. I can't change the 1, and we're concerned about N here, so we're going to keep that in there. That means the maximum value for L depends on N. So we already knew L had to be an integer, but if you know N, L can't be any bigger than N minus 1, right? So for N equals 4, L goes from 0 to 3. So this is telling us the allowed values of L are 0, 1, 2, all the way up to N minus 1. That's the answer to D. Okay, questions on that? And then E is, what's the smallest allowed value for N? Hint, what are the smallest allowed values for J max and L? Well, here again, I've got something solved for N up here on the board. And if I want to make N as small as possible, I choose the smallest possible J max. That's going to be 0. And the smallest allowed value for L is 0. And that means the smallest allowed value for N is 1. And other than that, we've observed that N is an integer, and it can actually go up by integer amounts because, L can jump up by integer amounts, so can J max. So it's an integer greater than 1. So that means that N is equal to 1, 2, 3, and there's no limit on how big N can be. Okay, and we've already got our given L, M is in the collection minus L plus 1, all the way up to L. Okay, so that's our full collection of allowed eigenvalues for the definite energy states. Okay, so there they are. We've got the collection of allowed N's. And now an interesting fact is that the energy, of course, doesn't depend on M or L. We talked about, it depends on M, the mass, but it doesn't depend on that quantum number M, which is somewhat confusing, possibly. So it doesn't depend on the quantum number little m, and we talked about last time that it never will. It just cannot because of the way the separation of variables occurs. But we saw in the spherical infinite well that E did depend on L. In this case, E doesn't depend on L. There's no L's sitting in this formula. It only depends on N. And that means there's some degeneracy. In other words, there are lots of different states with different L's and different M's. If you take N equals 8, L can go from 0 to 7. And then for each L, there's a whole lot of M. So there's a whole lot of degeneracy. Same energy, lots of different linearly independent states here. Let's figure out what the degeneracy is for this. So if you do the counting up here, we could say for each L value that's allowed, and we have N L values, right? L can go from 0 up to N minus 1. That's like from 0 to 5 minus 1 would be 5 values from 0 to 4. And then for each L value, we have 2 L plus 1. You can count it up, right? We go from minus L to L, plus we've got the middle value. So I've got L of them over here, L of them over there, plus an extra one. That's 2 L plus 1 M values, given that L's got to be an integer. And therefore, we can figure out what the degeneracy level, how many different linearly independent states there are for each energy. And here's how we do it. We have to say, add up for all the allowed L values for that particular N, the number that represents how many M values there are, okay? So when you write out this series, this is like 1 plus 3 plus 5 and so on, up to the upper limit is N minus 1. So I get 2 times N minus 1 plus 1. And if you simplify that, you get 2N minus 1. And that series, though it may not be familiar to you, it can be thought of geometrically like this. If I have the series 1 plus 3 plus 5, I can line them up like this, and I can say 1, 3 fit here to make a square so far, 5 more make another bigger square, and then so on up to n minus 1. Here I've taken n to be 4 in this case, right? In the picture here, I'm imagining n is 4. 2 times 4 is 8, minus 1 would be 7, would be the next term to appear there. So this picture corresponds to n equals 4. And the series that we're trying to add up is this, how many dots there are in there. Well, we can see if there are n dots this way and n dots this way, the total number of dots is n squared. So amazingly, that finite series adds up to n squared. There are other ways to prove that, but I like the geometric kind of proof. Can't remember if that's what Griffiths does in the book or not. Okay, and so that means given an n value, there are n squared different states that have the same energy. They're going to have different L and M values. N determines the energy, but there are lots of different L's and M's. The bigger n is, the more degeneracy you get. Now, these V of rho functions, again, are just polynomials. They're infinite power series where we caused it to terminate at a finite level. So that means they're polynomials. The generic name for them is the associated Laguerre polynomials. I don't know the origin behind this horrendous set of indices here, but in terms of our n and L, the way they are usually denoted is with the subscript n minus L minus 1 and a superscript 2L plus 1. So if you know those two numbers, you can back out what n and L are because you have two equations and two unknowns. But for reasons that I don't understand, that's the traditional in mathematical physics. These functions were known well before the hydrogen atom kind of was discovered for reasons in mathematical physics. Okay. And so we'll look at the combined radial function with these polynomials and the power function and the exponential function put in all together in just a second. Okay. And sometimes people write rho in a different way, right? Rho, we said, is proportional to R. That was the relationship between rho and R. Instead of putting it in terms of kappa, sometimes people write rho is, that this, instead of writing kappa R, we already found out that kappa was proportional to 1 over n, and all the other constants that are in there are written as 1 over a, where a is called the Bohr radius. Okay, and so that means that we can write this in terms of the symbol a rather than all these other symbols that are in there, and that somewhat simplifies the formula. Okay. So if you look into it and try to figure out what the Bohr radius is, it's this. And well, there's a question we'll do in, oh, we're over time today. I forgot to look at the time. Guess I got carried away. Well, we'll do a worksheet problem that asks about the Bohr radius in just a moment. In a moment, I mean by tomorrow. So let's hold off there. We've got our basic solutions now. And the only question is to look at these polynomials, try to get some intuition about the zeros of these functions, and then think about how to write any given state, bound state, as a linear combination of all of these states. But we want to visualize them first in the way that I'm sure you've seen these pictures that look like these probability density functions like this. Hopefully you've seen something like that before. So we'll try to make sense of those given our solution tomorrow.
Have a good day.
All right, see you, Elvis. Again, thank you for your patience while I figured out, or didn't really figure out, my drive problems, but I got something that was close to the set of slides I wanted to show to you, so that's good. Anybody have Homework questions. You're welcome to stay on now. I don't have another class today, so that's good.